Okay, so finally, I want to show you a deterministic algorithm. So this is an algorithm which does not work by tossing coins, and it has no uh, randomization in it. And but it turns out to be a bit trickier, and the goal is to find an approximate median. Okay? So let's see how this works. Okay, so recall the definition of an approximate median. It's you're given some unsorted array A. You want to find an x, which is one of the elements of the array, such that at least n by 4 elements are less than or equal to x, and at least n by 4 elements of the array are more than x. Okay, so that's what we mean by an approximate median. Right, so this is an algorithm that came up in 1973, and it was by Blum, Floyd, Pratt, Rivest, and Tarjan. Put up the names because these are all like stars in the field. Okay, so and it's remarkable that they all wrote a joint paper about something as basic as this. Okay, so it also shows that the algorithm is pretty clever. Right, so. Okay, so how does the algorithm work? Okay, so it works by saying that I have this array of length n, this large array of length n. I break it up into pieces. Okay, so the number of pieces is not terribly important, but it should be a reasonable number. Okay, so let's say I break it up into chunks, 5 chunks, each of size 5. Okay, each of size n by 5. That is okay. So 5 chunks, each of size n by 5. It turns out that this is a surprising application of divide and conquer. Okay, so I do this, and then let's say I gather these chunks and write them down one below the other. Okay, so I have n by 5. I have let's call these arrays. Yeah, so these are just 1, 2, 3, 4, 5. So there are 5 of these arrays. Okay, and each has size n by 5. I just wrote these down one below the other. Okay, so now I would like to actually view this as some kind of a matrix. Okay, so it's like a 5 times n by 5 matrix. And now I want to look at the columns of this matrix. Okay. And let's say I sort the columns of these matrix in increasing order. Okay, so each column I sort it independently. So I look at all of these elements, and these are just 5 elements in this column. So I just sort them by some kind of a brute force algorithm. Let's say I use merge sort. Okay, so there are only 5 elements, so any sort just takes constant time. Okay, so this is constant time per column. Okay. And you do this independent of columns. Okay, so every column independent of the other column. So each column you sort it just independently, just sort the elements among themselves. Okay, and you do them in order. Okay. All right. So now what you have is a matrix where each column is sorted in increasing order. So rows, you can say nothing about them, right? Like you can't say anything about this entry was this entry, or this entry was this entry. Nothing of that kind can be said. All you know is that each column is in increasing order. Okay. So now the key thing is, after you've done this, let's look at this middle row. Okay. How many elements does it have? Of course, it only has n by 5 elements because you didn't mess with the matrix. So it just has n by 5 elements. And I look at this middle row. Okay. So these are, if you think about it, uh, these are the middle elements of each column. Okay, so they are in some sense the median of every column. Okay. Now what I want to look at is this array of medians. Okay. And now I want to claim that for this array, I want to look at the median of this array. Okay, so what does that mean? In this case, find the median element, or equivalently the n by 10th smallest element. How do I do this? It's a smaller array, so I can do it by recursion, right? So this is an array of size n by 5, so I can do it by recursion. Okay, so let's say I do that. Okay. All right. So what I've done is I've rearranged these elements into a matrix. Okay. Rearranging, of course, only takes O of n time. Okay. And I have sorted each column. Okay, so O of n, one time per column, so overall it takes O of n time. Okay, and I'm looking at these third rows, and I'm making a recursive call onto an array of size n by 5. Okay, so this takes time t of n by 5. I'm just noting down these right now. They're not terribly important right now. We'll write down the recurrence later. But first, what I want to say is that I found some element over here, right? So I looked at these n by 5 elements and I found some element which is supposed to be the median of just this middle row. Okay. Now the claim, the main theorem that these guys observed is that the element that you found using this process, which is the final element, the output of this, let's call this x, is actually an approximate median for the entire array A. Okay, so if I were to look at the original array A, the element that I found like this is actually an approximate median of this. So it should strike you as a bit surprising, right? Because you're doing this weird reorganization of this array, and then you're looking at these middle elements in each column, and you're looking at the array formed by that, and you're taking the median of that. Okay? So that's what you're doing. Okay? But the proof is actually very simple. Okay? So the proof is what I found is this number x. Okay, so this number x is the median of this middle array, this light blue array. Okay, what does that mean? Right, so what it means is that, so let's give this array some name. Okay, so let's call this C. Okay, or better still, let's give an array to the matrix. So let's call this let's call these A1, A2. These are subscripts, not to be confused with array indices. Okay, so these are subscripts, and this is A3. Okay, so X is the median of A3. Okay, what does that mean? Means that there are roughly half of, so A3 itself has n by 5 elements. So half of those are less than or equal to x, and half of them are more than x. Right? So that's the definition of a median. Okay, so there are n by 10, that's half of n by 5, elements of A3 smaller than or equal to x, and n by 10 elements of A3 more than x. That's just by the definition of the median. Okay, and so what does that mean, right? So I want to claim that this implies that there are many more than n by 10 elements that are less than or equal to x in all of A. Okay, and how do I do that? Right, so this is x. Let me take some y that is less than x. Okay, so I took let's take some y in A3 that is less than x. Okay, okay, take y in A3 that is less than x. Okay, now the key thing is that because these columns were sorted, okay, So the two elements above y are also less than x. Okay, because y was less than x. So the two elements above y were also both less than x. Okay, and this is true for any y in A3 that was less than x. Okay, so what that means is that this implies that 3n by 10 elements of A, which is the full array, are less than or equal to x. Okay, and I just gave you the proof, right? Because I took, let's say you take any y that's less than or equal to x, two elements on top of it are also less than or equal to x. So for any y in A3, I get two others. So overall, there are like 3 times n by 10 elements that are less than x. Likewise, if I took any z that is more than x, and any z in A3 that is more than x, two elements at the bottom are also more than x because this is in increasing order. They were bigger than this element and therefore they were bigger than x as well. Okay? And that's a very beautiful argument, but it's also a very simple argument, right? So what this shows is that this implies that and 3n by 10 elements of A more than x. Okay, so and that completes the proof, right? Because 3n by 10 is actually more than n by 4. Okay. I allowed a little slack because maybe there's n by 10 plus 1, n by 10 minus 1, things like that. So I allowed some slack over here. But this 3n by 10 is more than n by 4. So, okay. So that's why this whole thing follows. Okay. So it's a very simple proof, but it's a very clever proof as well. Okay. So that's what this shows, right? So what this shows is that this algorithm ends up finding an approximate median. Okay, so let's now look at the running time of this algorithm. Okay, so this is the proof of correctness. Let's look at the running time. Okay, so note that now the approximate running time is no longer I mean, it also involved a recursive part. Right? So this is what we wrote over here. Right? So we carefully worked out the running time of this whole process was O of n plus t of n by 5. Okay, so f of n, which we denoted by the running time of the approximate median, that was something of this kind. Okay, so let's plug that back in. Okay, so let's plug it back in. So you get that t of n is less than or equal to t of 3n by 4 plus this f of n plus O of n. Right, so that's what we had before. So you get t of n is less than or equal to t of 3n by 4 plus n by 5 plus cn, okay, for some constant c. Now, what is this, right? So this is a weird recurrence. It's not very easy to solve, but I want to claim that this is at most uh, this the closed form. The claim is that t of n is less than or equal to alpha cn for some constant alpha. Okay. And I'm going to do this by a guess and prove kind of method. So I've already guessed it. So let's just prove by induction. Okay. So let's prove by induction. What does it take? So assume it is true. The base case is, yeah, let's do the base case first. Base case is immediate. Okay. T of 1 is just 1 or something. I mean, it's constant. So I set alpha to be more than that, and base case would work out. See, alpha equals 1. C, remember, is some constant more than 1, so there's a lot of slack for the base case. Okay, so assume it holds for numbers less than n. Okay, And now consider this n. So now 3n by 4, n by 5, these are all less than n. So what I get is that by the inductive hypothesis, okay, so we get that T of n is less than or equal to alpha times C times 3n by 4. Okay. So by the inductive hypothesis, T of 3n by 4 is less than or equal to alpha C times 3n by 4. And so that's what the inductive hypothesis is. So I have this plus alpha C times n by 5 plus Cn. Okay. And so what is this? So this is alpha C times, I think it's like 19 by 20 times n, okay, plus Cn. Okay. And for my induction to work out, okay, so I want to claim that this, for my induction to work out, I want this to be less than or equal to alpha Cn. Okay. And can I pick an alpha for this, for which this happens, right? And you can easily see that picking alpha equals 20 suffices. Okay, so what we've shown by induction is that overall the running time is less than or equal to 20 cn. Okay, so or rather overall we get T of n equal to 20 times cn. Okay. So you might be thinking that this 20 is a pretty large constant, and in fact, apparently the original paper gives a fair amount of analysis as to how to improve this constant. And they can bring this 20 down, and in fact, actually even this 20c, they do a careful implementation of the overall recursive thing, and they end up with a constant like 5.8 times that. Okay, so for that part, there's a lot of engineering involved. It's a case by case messy analysis, but they show that it's only like 5.8 n. Okay, and they do this because this is such a very basic problem. Okay. All right, so that completes what I wanted to say about this problem. Okay, so it's a beautiful algorithm, like the overall thing, the deterministic one, and what it shows is that the selection problem, like if I want to solve, if I'm given an unsorted array and I want to find the kth smallest element, I can do it in only O of n time. Okay, and so I don't need to sort in particular. Okay, so yeah, you have a couple of homework problems that are based on this intuition, based on this algorithm. More of using this algorithm as a black box, just to show you its power. Okay, so yeah, so with this I will end the video, and yeah, it concludes the makeup lecture.